Hello everybody, my name is Bilal Kourani, and today I'm going to present XModal-ID, a system that can use Wi-Fi to identify people through wall from video footage. This work is in collaboration with my lab mates Chitra and Herbert and our advisor Professor Yasmin Mustofi at UCSB. In this work, we're interested in enabling Wi-Fi signals to identify a person through wall from a candidate video footage. Let's first see a motivating example for this problem of interest. Consider this scenario. Law enforcement has a video footage of a robbery. They are suspicious that one of the robbers is hiding inside the house. Can a pair of Wi-Fi transceivers outside the house collect Wi-Fi measurements and determine if the person inside the house is the same as the one in the robbery video? In this work, we show for the first time that this is indeed possible. Let's first take a look at the state-of-the-art in person identification. While there could be many different ways for identifying a person, the way a person walks or their gait has recently been used for identification. And the motivation behind that is that the way each one of us walks is different. And hence, gait can be used as a signature or a unique identifier of the person. This has opened up possibilities for using RF signals to identify a person, based on how this person's way of walk affects the wireless signals in the environment. And many different systems have already been designed for this purpose, like Wi-Fi U, Waihu, FreeSense, among many others. However, there is no prior work that enabled Wi-Fi to identify a person from a video footage. Moreover, all the previous work on person identification requires the collection of training data of the person that we eventually want to identify. So in this paper, we propose XModal-ID, a system that can determine if a person in a Wi-Fi area is the same as the one in a video footage. Our system doesn't need any prior Wi-Fi or video training data of the person to be identified. It uses only the Wi-Fi CSI magnitude measurements on a pair of Wi-Fi transceivers, and it doesn't need any knowledge of the operation area. And hence, it can be seamlessly used to identify new people in new areas without any need for retraining. As such, it can be used for many different applications, like in security, as I mentioned, or in other applications like personalized service provisioning, for example. Let's now see how we have enabled this. As I mentioned earlier, the way each one of us walks is unique. But how can we capture this gait information from a video and transfer this information into the Wi-Fi domain? In this work, we propose a way that for the first time can translate the video content into the wireless domain. Consider this video of a person walking. We draw from the recent advances in computer vision, and we utilize a human mesh recovery algorithm that extracts the 3D mesh of the person in each of the video frames, thereby giving us a model for the person's walk as a function of time in 3D space. Then, using this generated mesh, we can simulate the Wi-Fi signal that would have been measured if this person was walking in a Wi-Fi area. And we do so by using the Born electromagnetic wave approximation, which essentially treats each point in that mesh or each point on a person's body as an independent reflector and sums up all the reflections from all these points at the Wi-Fi receiver to generate the simulated Wi-Fi signal as a function of time. Next, consider this area where a person is walking. A pair of Wi-Fi transceivers are inserted outside of the area, where the receiver is collecting the Wi-Fi. To extract the gait information of this person, we propose to utilize a combination of short time Fourier transform and Hermite functions in order to generate a spectrogram of the received signal. A spectrogram is the frequency content of the signal as a function of time. And because the frequency content is related to the speeds of different body parts while the person is walking, this spectrogram implicitly carries the gait information of that person. Now that we have the gait information of the person in the Wi-Fi area in a form of a spectrogram, we can go back to our earlier video to Wi-Fi pipeline and similarly generate a spectrogram of the simulated Wi-Fi signal for the person in the video. In order to determine whether the two spectrograms belong to the same person or not, we extract a set of 12 features that are related to various time frequency characteristics of spectrograms and compute the distances between these features. And we finally use a simple one-layer neural network that combines all these features into one final decision on whether the two spectrograms belong to the same person or not. And during the training phase, the goal of the training is for this small neural network to find the optimal combination weights of these features, as not all of them might be of the same importance. This figure right here shows an overview of the processing pipeline for XModal-ID. In order to validate our approach, we carried out a lot of experiments on our campus. We started by recruiting a set of 10 subjects for training purposes, and we collected their Wi-Fi data in these two areas, and we collected videos of their walking in this area. And we used the Wi-Fi video pairs of these subjects to train the network. In order to show the generalizability of our approach, none of these training subjects and none of these training areas will be later used in the test phase of our system. Now let's see a test experiment. In this test area, a test subject is walking while a pair of Wi-Fi transceivers are outside the area collecting the Wi-Fi measurements. Given the video of a person walking in another area, the task of XModal-ID is to determine if the person in the Wi-Fi area is the same as the one in the video or not. When tested on more than 380 Wi-Fi video pairs, when the Wi-Fi data is collected in this area, and we collected the data from 8 different test subjects, all of whom are not part of the training set, our system achieved a binary identification accuracy of 83%, which means that 83% of the time, our system made the correct decision on whether the person in the Wi-Fi area is the same as the one in the video or not. In this other lounge area, again, we collected the Wi-Fi measurements in a behind-the-wall setting. And we have more than 740 Wi-Fi video pairs of the 8 test subjects. And our system achieves an accuracy of 82% in this area. In this third area, also we collected the Wi-Fi data in a behind-the-wall setting. And our system achieved an accuracy of 89% when tested on 360 Wi-Fi video pairs. Additionally, we collected Wi-Fi data in a line-of-sight setting, in which the Wi-Fi pair was placed in the same space where the person is walking, with no obstacles or walls. In these two areas where we collected the data in such setting, our system achieved an accuracy of 88%. So in summary, we tested our system on 8 different test subjects in 5 different areas, all of which are not part of the training set, and we achieved an overall accuracy of 85% when tested on more than 2,000 Wi-Fi video pairs. Moreover, we tested our system in a ranking setting, in which the system is giving the Wi-Fi data of a person in a Wi-Fi area, and instead of one video, it was given the 8 videos of the 8 different people. And the task is to rank or sort all the videos in terms of how similar they are to the Wi-Fi data. When tested on more than 280 such ranking tests, in 75% of the time, our system ranked the correct video or the video of the actual person in the Wi-Fi area as the top rank, or the video that is most similar to the Wi-Fi data. In 90% of the time, the correct video was in the top 2 ranks, and in 97% of the time, the correct video was in the top 3 ranks. Note that because we have a group size of 8 people, a random hit would give us a success rate of mere 12.5% in this case. So to conclude, we propose XModal-ID, a system that can determine if a person in a Wi-Fi area, possibly behind a wall, is the same as the one in a video footage. It uses only the received power of a pair of Wi-Fi transceivers, and it doesn't need any prior Wi-Fi or video data for training purposes of the person that we eventually want to identify. And it doesn't need any knowledge of the operation area, and we have extensively validated our approach on different test subjects and different test areas and achieved an overall identification accuracy of 85% when tested in different real-world scenarios. Thank you.